Hello all, as we continue our journey looking at circular functions. Today should hopefully be, well, it will definitely be shorter than the last video, but on the shorter side of things, as we look at addition of ordinates for circular functions. So what is addition of ordinates? Addition of ordinates is a method we use to graph a function that is a composite function. That is made up of the addition of, say, what we could break down to be two simpler functions. So in this case, we may have a simple function y1, which is equal to 2 sin x, and y2, which is equal to 3 cos 2x, and they would have both the same domain. Now, what we could do is make some new function. In this case, it's just called y, but let's use sort of our function notation a little bit more. We might call this g of x and this h of x, and we might want to make some new function f of x that is equal to g of x plus h of x. From that, and in this key thing here is the plus sign, is we're not multiplying them together. We're not having one function inside of another. We're just adding these two together. Technically, we'd also do subtraction. We can do a subtraction here, and we can do a subtraction of ordinates. The process is exactly the same, but it's when we have one plus the other. And the way you can think of it is, well, we have one function, we get a result out of this, thinking that function is sort of machine, input a number, we get something out. So we might put a 2 in. Now, out of g of x, we might get a 3. And then out of h of x, we might get a -1. Let's not make it -1. Let's make it -half. Okay. Well, if we put a 2 in and we got 3 out and -half of those individually, when we then add them together, we then clearly get 2.5. We can apply this idea of let's resolve or solve each of these or evaluate each of these functions individually, and then because there is this great big addition between them, we just add those results together and that gives us our final result, and that makes sense. We can do that with ordinates or coordinates. We can find the coordinates or results of just g of x first, which is this y1 here. We can then go on and find substitute in again all those same values for h of x or y2 here. And if we add them together, we get our final answer, or as we used in our function notation, f of x. So by substituting in 0, I can get the black color I wanted. If I substitute 0 into y1, I get 0. If I substitute it into y2, I get 3. Add those together, my final result is, of course, 3. And I can do that again over and over and over for a variety of inputs. How many inputs you want to do that for depends on, in particular, sort of the size of the period of circular functions. You don't want to, if the whole period is pi, you don't want to do pi intervals because you're going to be losing. You might get, if you just did pi, you might get, oh yeah, it's here and it's here, but you're losing all that detail in between. So you're going to want to normally do probably at least quarter period intervals to resolve enough detail to actually get accurate graphs. And our final thing that we're going to plot is pi on 2 and the -1. So effectively, to do one addition of ordinates graph, if we want to plot, not y1, if we want to plot y, you first have to figure out all the y1 values, all the y2 values, then add them together. So it's almost like plotting 3 graphs, or 2 graphs first, add them together, get your third graph. So there's a bit of work there. So let's have a look at an example. Again, using these, it's the exact same functions. Okay, we have 2 sin of x and 3 cos 2x, and the first graph is represented in the yellow. I don't have yellow. We'll call it the green. It's this green here. The second graph is plotted as no, I've got this around the wrong way. Hold on, let me make sure I'm getting this correct. No, that was right. Green, yeah, it goes up to 2. down to -2. The green is that one. The blue, no, the dashed red is this one, 3 cos 2x. Yeah, it goes up to 3, down to -3. And then the combination of them is blue. So if we look at the first data point, we get 0 plus the 3 gives me 3. Let me go along. Let's plot the y1 values, which we said were green. So 0, 0. We plot that point. At pi on 4, we get square root of 2. Pi on 4 is about there. We done that one. At pi on 2, we got 2, which is there. Plot that point. Pi, we get 0, which is that point there. 3 pi on 2, we get -2. We've got that point there. We go through, you would go and plot all the y2 values. So 0, 3, we get there. Pi on 4, we get 0, which is there. Pi on 2, we get -3, which is down here. Pi is 3, which is up there. And then 3 pi on 2 is -3, which is down there. And then all you're going to do, of course, is you could have done this with the table of values. You can also do it plotting it out like I've just done there, is you'd add all the values. So if I look, this line here, 0 plus 3 is, well, 3. Here I've got 0 plus root 2, so that adds up to there. Here I've got, looking at this line, I have 2 plus -3. 2 plus -3 gives me -1, which happens to be there. On this line, I have 0 plus 3, so that means my point is going to be 3. And then if I come to 3 pi on 2, I have a point at -2 and a point at -3. Add those together, I get -5. Play connect the dot, and you get your resulting blue graph. So if we just want to plot the final result, you could just find all these values, table of values, add them together, and then just plot the blue dots. Either method will work, all graphically, all table. So let's have a go at that. So this is where you're going to have to work on knowing exact values, and also hopefully noticing if you notice patterns and periods, then that will really help. So for y, let's call this y1, and we'll call this y2. We'll notice A is 3, period is pi. For this one, period is 2 pi. So we can use that to help repeat our values if we notice patterns. So -pi, so sine of -2 pi is 0, so that's going to be equal to 0. That's 3 by 0, so it's equal to 0. Sine of 0 is also going to be equal to 0. Sine of 2 pi is going to be 0. What other ones can we knock out? -pi on 2. Put that in there. That's going to be the same as -pi. That's also 0. That's 0. Okay, -3 pi on 4. So -3 pi on 4 in there. 2 and the 4 cancel, leaving 2. So that's -3 pi on 2. -3 pi on 2 is around to there. So that's going to be 1. Do the same thing for -pi on 4. -pi on 4, cancel, cancel. You get -pi on 2, which is around there. That's -1, and that pattern will repeat. Now we can just do cos, and cos is it's just the standard cos function, so it should be pretty quick. Cos of -pi, going around here to -pi is -1, -3 pi on 4 is there, so that would be negative root 2 on 2. -pi on 2 is there, so that is 0. -pi on 4 is there, that is still negative. No, cos, that would be positive root 2 on 2. Cos of 0 is 1. Cos of pi on 4 is root 2 on 2. Cos of pi on 2 will be 0. Cos of 3 pi on 4 over there will be negative root 2 on 2. And cos of pi will be negative 1. Now we just add them all together. Negative 1. 1 take away root 2 on 2. 0. Negative 1 plus root 2 on 2. 1. 1 plus root 2 on 2. 0. Negative 1 take away root 2 on 2. And negative 1. For this, it's clear to see that if we have a rough decimal estimate of what root 2 on 2 is, will be really helpful. Root 2 is equal to 1.4. Divide that by 2. So we're going to get roughly 0.7. So we can make an estimate that that's roughly about 0.3. This is roughly about negative 0.7. That's roughly 1.3. That is roughly negative 1.3. And we have all those, we can now plot them. So negative pi is negative 1. Negative pi is 1. So there. Negative 3 pi on 4 is about 0.3. Negative 3. And again, this grid is not nicely divided like in the previous video. 3 pi on 4 is negative 3 pi on 4. Halfway between those two. 0.3. Yeah, there. Pi on 2, we got 0. Negative pi on 4, we got negative 0.7. Out there. 0 is 1. Up there. Pi on 4 is 1.3. Pi on 4 is 1.3. About there. Pi on 2 is back to 0. 3 pi on 4 is negative 1.3. There. And 0 is negative 1. There. Now we just need to connect the dots. So we get some sort of function that looks like that. So it's a bit weird there. There's waves, and you can sort of imagine it's waves within waves. We're applying one on top of the other. But that's our final graph. And you would want to label the points you found, especially if some of these intercepts we had, so you'd want to label those. That's it. That's it. 6H, nice and short, 13 minutes. glad it's a little bit shorter. The hardest bit is just tedious work, working through repetition, addition of ordinates. This idea of applying one function on top of other can also work not just for circular functions. We could have done this exact same thing for instead 3 sine 2 theta plus e to the x. And you'd have to substitute in, make a table of values for 2 sine 2 theta on top, but this one would be e to the x. Now let's have a quick think about what that would look like. So 3 sine 2 theta, if we drew that on here, and this is going to be handy because this is going to be in the SAC. Adding sine on top of an exponential, what's that going to look like? Well, an exponential is looking like that, and then we're adding a wave on top of it. So what is that going to look like? Well, it's going to go something like that. Now, where in real world do we get a situation like this? Generally, stock markets go up, but they don't just go up in a straight line. they're working up like that. And also stock markets, if you look over a long enough period, and if you look at crypto stuff in particular, they're working on an exponential scale. So they're on a wavy sort of line going up exponential. So that's where you could have a combination. What happens if we flipped the exponential about the y-axis? We would have something like that. So our final result will look like this. That could be the amount of alcohol in your bloodstream or amount of caffeine in your bloodstream after so many drinks. It's coming down. It can be working up and down a little bit depending on your heart rate, all sorts of things. If you had another drink, you could change those scales to make it. So yeah, if we went with that caffeine style one and we changed the overall, the amount of caffeine in your body reduces, but if you have another drink, well, it's going to spike up, come down, have another drink, spike up, come down, have another drink, spike up, come down. And that's where you can apply that to figure out what sort of period you need to simulate, because this time could be in hours. This could be 1 hour. That could be 2 hours. Same for medicine. The amount of medicine in your body reduces, but if you have a dose of something, painkillers maybe, Panadol, spikes up. And if you leave it for a while, it's going to drop down, have some more spikes up, have some more spikes down. If you just got a headache, that's fine. You might want that decrease, but if you want to keep your rate up, you need to keep taking it much more often. But that's where this idea of addition or adding functions on top of each other becomes really applicable in the real world. Okay, that's all that there is. If you have any questions, like usual, stick in the comments below, Google Classroom, ask in class, or shoot me an email. See ya and have a good evening.